To finish up section 3, sorry. So we're finishing section 15.3. Last time in section 15.3, we had talked about these 4 properties of logarithms. I'm only going to reference these first 3 because they're the 3 that we need in order to do these problems we're about to talk about. So those were the product, quotient, and power properties. Again, we talked about these at the very end of last time, but since we're going to refer to them multiple times here in the upcoming examples, I figured I'd write them down again today. These 3 properties we're going to use rather often in doing, the homework associated with this section, and then also again in the following sections on solving, we'll be using these properties here on occasion. So these are 3 that you'd probably want to get committed to memory. These are good ones to kind of make sure you know, just like the exponent properties are good ones to know, because they just kind of come up over and over and over again, maybe often when you least expect it. Particularly if you're going to be a calculus student, we end up using logs and these properties of logs to do a couple of different calculus techniques to make our lives easier. You're like, what? How is a log going to make calculus easier? It's like, well, we'll show you next year. All right. So there's 2 major types of problems that, bless you, you're welcome, that we're going to talk about here today. Those 2 types of problems are called expanding and condensing logarithms. So if we want to expand a logarithm, what we're going to do is we're going to start with 1 logarithm and rewrite that 1 logarithm using as many logs as possible. So typically the order in which we apply our properties when expanding is going to be quotient first, and then product, and then power properties. And because we are working on starting with 1 log and creating many logs, we're going to work our properties from left to right. So the product property, which you're going to be looking for, is multiplication inside the logarithm, quotient, division inside the logarithm, and power property, an exponent inside the logarithm. The other type of problem that we'll talk about is condensing. Condensing is going from many logs to as few logs as possible, ideally 1, but maybe not. So the order of properties that we'd use there is going to be reversed. So typically it's going to be power, product, and quotient. And because we're looking to go from many logs to few logs, we're going to be using the properties from right to left. So the product property, you'd be looking for addition between 2 logs. The quotient property, subtraction between 2 logs. And the power property, the coefficient on a log. Yes, Eddie. Sure thing. And again, with the order that I've written these properties, this is the typical order. There may be situations where, like, we have to look at, we have to be a little bit careful, or the way things are implied, there's an implied order going on, or maybe there's a set of parentheses that are telling us, oh, we really should do this thing first because it's in parentheses, even though it may be the wrong order, whatever. But we'll kind of cross those boats when we come to them here in a few moments. Okay, so let's start with some examples. So let's do some expanding examples first. So these are expanding problems to start. Our first example problem is log base 3 of 4x. So since we're expanding, the order that we want to consider the properties are quotient, product, and then power. So looking at this, is there a quotient property present? No, because there's no division going on inside the logarithm. Is there a product property present? Yeah. How many product properties do you see? One, because there is one multiplication symbol there. Okay. So we can apply the product property. Oops. Forgot that 3. So that gives us log base 3 of 4 plus log base 3 of x. Now I've created 2 new logs, so I need to start my checking the properties all over again at the beginning. So I'm going to be looking at log base 3 of 4 and log base 3 of x, and first checking for quotients. Of course there's not. Products? No? Okay. Powers? Okay. Look again closer. Notice the number 4 is not a prime number. It's a composite number. I could be thinking of 4 as 2 squared. So there is a power property there hiding on you. Whenever you have an argument inside the logarithm that's not a prime number, we will either have some power or product property, or maybe a combination of the two that we can do. And again, if we're looking to expand this as fully as possible, the expectation would be that you would take log of 4 and write it as 2 log 2. Or if you thought about it as a product property, you could have log 3 of 2 plus log 3 of 2, but though you could combine those like terms to write it as 2 log 3 of 2. Okay. Mr. Kulik, that was kind of a nasty trick there you just pulled with that coefficient. Well, you know, like, it's not so nasty if I'm showing it to you first, right? It'd be nastier if I put it on the test without showing you the trick. You know, try not to do that. Next example here. Is log of 3ab. I'm sorry, 3ab to the 5th. Yeah. It's the end of the day, folks. Actually, I just got done eating an ice cream sandwich, so like the blood sugar level is kind of going all over the place, and it's a little, everything's a little foggy. You know how you get? You eat a big meal. Yeah. All right. First things first, we look for which property? Quotient. Do you see any? No. Okay. Next we look for product. Do you see any product properties? How many? 2. Because there's just 2 multiplication symbols there. So there are only 2 product properties. Feel free to apply both of them at the same time. Everybody clear as to like what kind of happened there? There's no sense in applying them one at a time. It's just kind of a hassle to do it that way and writing extra lines. Let's do them all at once. Happy? Okay. We created new logs, so we start back over at the beginning. So looking at log 3, log a, and log b to the 5th. First check for quotients. Any of those? Then we check for products. Any of those? Okay, last we check for is powers. Do you see any of those? How many? 1. In which log is that occurring? The last one, the third one, b to the 5th. Very good. So that's going to just rewrite that one as 5 log of b. Okay. All right, next example. Let's say we have the natural log of the square root of x cubed minus 5 all over 2x. What's the first thing I check for? Quotient. Do you see any? Yeah, clearly there's some division going on here. So when we write the quotient property, we write the log of the top, or the numerator, minus log of the denominator. Order matters there because order matters in subtraction, so we have to have the numerator minus the denominator. Everybody cool with that? All right. We got some new logs, so again, looking at the natural log of square root x cubed minus 5 and the natural log of 2x. We need to start at the beginning looking for quotient properties. Do you see any of those? Oh, of course not. Next up, we look for product properties. Do you see any of those? Yeah, how many? One. And where is that occurring? With the 2x. Okay. My pen stopped working there for a second. So when I'd write that, I'll write it there. Does that look good? Oh, does it look good? Lily?
Don't you have to take the radical out?
Well, right, there's still more to do, but is what I've written correct? The answer is no. There's a mistake here. Mr. Kulik did it on purpose because this is a mistake I see a quarter to a third of students make consistently, even after I show them what the mistake is that they're making here. The mistake is in the previous line, natural log of 2x is negative. So when I apply the product property, everything that's created still needs to be negative. So I really should have written natural log 2 minus natural log x. Whoa, Mr. Kulik. It's a good thing you're showing me that. I would have made that mistake. The hint that you're going to have to distribute the negative is when you have multiplication going on in the denominator of your fraction. So that's what I'm looking at in the beginning of the problem, knowing already that I'm going to have to distribute negatives through, which helps, right? That there's a little bit of a, yoo-hoo, going to have to do that warning in the beginning. You know what I'm saying? Okay. So as Lily mentioned, there's still some power property to do. The power property is associated with the square root there. What's the power for a square root? 1/2. Yeah. So since the square root is around everything inside of the log, I can use the power property to pull that out and write it there. Everybody okay with what I've done? Is there anything else that I can do here? Can I do the power property on the x cubed? No. Why not? Because there's also the minus 5 next to it. Very good. When you look at the power property, the power must be applied to the entire argument of the logarithm. So everything that's inside that logarithm has to be to that power. The 3 is applying only to the x. As a hypothetical, would I be able to use the power property on that? No. The reason is that that is not the same as that, because we know exponents don't distribute. What could we do with x cubed minus x to the 5th? Or I'm sorry, x cubed minus 5 to the 3rd? You could factor that as a difference of 2 cubes and then use the product property on it. That would be okay. That you could do. Remember the difference of 2 cubes factoring pattern from Algebra 2 was this guy. I wouldn't ask you to do that in I don't think that happens in the homework, and I wouldn't ask you to do that on the test. But since we're talking hypotheticals, let's talk about what we could do, right? Just in case anybody will go back and look at that and it's like, what the heck is all this down here doing? That's just hypothetical. Okay. We feel okay about expanding? That's basically all the tricks I can think of. Not too bad. Or most of the tricks I can think of. I think I saved some, but I'm sure they'll come up. I can't do all the tricks for you guys, Sometimes we have to find them naturally as well. All right, so let's move on to condensing. So again, with condensing, we're trying to take many logs and write them with as few logs as possible. Since the directions are essentially opposite that of expanding, the order in which we apply our properties is also the opposite. So condensing, we go power, product, then quotient, the reverse order of expanding. And when we use the properties, we're looking at the right-hand side of the property rather than the left-hand side. So product property, we're looking for addition outside the logarithm. Quotient property, we're looking for subtraction outside the logarithm. And power, we're looking for a coefficient on the logarithm. Okay, condensing, first thing we do is think of these or look for powers. Do you see any power properties? Yeah, how many? 2. On which logs? The second and third one. Yep. So we could write it like that. Everybody feel good with that? Anybody want to try to do this a different way? There's an alternative way you could approach this. Or alternative way you could apply the power property here. You could think of the power there as -2. If you like, it's doing the same thing. Both of these would be equivalent statements and would get you to the same spot eventually. So you could do it that way as well. Everybody cool? It's a matter of preference on whichever you want to do. Okay, next up, we look for product properties. Let's just work on the left-hand one first, and then we'll come back and do everything on the right-hand one after we finish the left hand. Everybody's cool? Okay. So looking at the left hand, do we see any product properties? So again, when we're doing this, we're looking at the left-hand sides. So we're looking for this kind of a situation for a product property, right? We're not trying to make more logs, we're trying to make less. Do we see a product property? Yeah. Between which logs? Yeah, the first and second logs. Absolutely. So we can apply the product property there. Cool. The last property we need to look for then is the quotient. Do we see any quotient properties? Look carefully. The answer is no. But Mr. Kulik, I'm staring at a frickin' subtraction symbol right there. Why is there no quotient property going on? The bases of the logarithms are not the same. You'll notice for both quotient and quotient and product properties require the bases to be the same. So this is actually as far as we can go on this one. We'd be stopping right there.
So the fourth property has
The change of base
that doesn't help.
would not help us here.
What do you use that for then? Why would you need to change the base?
So we'll talk about, I talked about that last time. It was quite useful prior to your calculator being able to do log of any base. Because originally, when I was a student, how we would do something like log base 2 of 3 is I'd use the change of base formula to write that as like common log of 3 divided by common log of 2. And then I'd have to look those values up in a table that was pre-computed and then divide them on my 4-function calculator. And later, as we got scientific calculators that had like common log and natural log button built into it, but not any log, I could do just, again, the change of base, but not have to look the values up from a table. I could type them into my calculator. And now your guys' calculator, you can do log of any base, and the calculator can just handle it. So it's not super useful to us right now. But I guess, like, if you want to get real fancy, we could use the change of base formula to get this thing combined, but it's going to get real ugly. I'd prefer not to go there. We'll just stop here. If you're interested, though, we can do it. I see how to do it. Do you want to do it?
How long does it take?
A minute.
Oh.
So this is what I would do if you wanted to go this route. So I'd want to write this as log of 4 x squared over log of 4 of 5. I would think about this just really now as a coefficient, like 1 over log base 4 of 5 times log base 4 of x squared. So that would make it a power property. And then we can do the quotient property here. That's a y cubed. And that's really like log base 4 of 5 radical of x squared. I guess that's a base 4 there. I guess you could do that. I would not expect you to do that. I would just, if the bases didn't match, I'd expect you to just kind of stop there. But you could. Again, I'll put hypothetical here around this whole thing. Because yick. Particularly this piece that I highlighted in yellow, noticing that's really just the same thing as a power. Not super obvious, since it's just a constant, whatever number log base 4 of 5 is.
Why is it 1 over?
Because it's in the denominator, right? So like I would think about this as this times,
Oh, I see.
you know what I mean?
Yes.
So that's why it's now a 1 over fraction. And again, we know that a fractional exponent means a radical. So like, yeah. Okay. If we did the right-hand side, again, we do our product property that's easy to spy. And I'm going to use my property of exponents to just write that as 1 over x squared. And that's as far as we could go with that now. Again, we can't do a product property because the bases don't match unless you wanted to do that change of base thing, and we'll end up at the same spot. but let's not. You know what I mean? Because it's like the same steps or whatever, you know? Okay. All right, let's look at the next one. 4 times natural log of A minus 3 times natural log of AB plus 2 times natural log of B. What do we start with? Power properties. How many power properties do you see? 3. It's worth noting that you have to be a little bit careful when you do 3 natural log of AB. The exponent of 3 needs to apply to the entire AB. Or if you wanted to take the negative sign with it, you could do that also. Somebody was excited about Taco Bell out there. So again, either way of doing that is fine, no big deal. Yeah? I'm going to do the left-hand side now all in a row, and then we'll come back and do the right hand all in a row. Cool? Okay. Next up, we've done the powers. We look for product. Do you guys see any product properties? Yeah? How many? 1? Great. And it's occurring between which logs? The last 2 is incorrect, actually. The product property is occurring between the first log and the third log. Wait, what? Why would that be the case? What's wrong with the middle log? It's got a negative sign in front of it. The power property or the product property requires both the logs to be positive. So the way to think about this is remembering that we can add things in any order we want. So I could think about it this way, and then it's much more obvious that, yeah, of course, the product property is occurring between the a to the or the log a to the 4th and log b to the 2nd. Mr. Kulik, that is some dirty tricks you're playing on me. But this is why we're doing the example, so I can, you know, get through all my best material on you guys. Right? These are the kinds of things like, oh, yeah, makes sense now that you showed it to me. Would definitely have tricked me if I would not have seen that beforehand. And then my last step would be quotient property, and nothing sneaky there. Worth pointing out to us that we can reduce that fraction just down to a over b. All right. How would have this looked different if we had taken the negative exponent or taken the negative sign with our exponent when we did the power property? Well, I think in this case, life becomes much less ambiguous, right? I just see 2 product properties. There's no ambiguity about which logs are part of the product property, right? Because everything is just being added. Feel cool there? I combine my like terms and then apply my negative exponent property and I'm done. That ain't bad. So taking the negative with the power property can be, avoid some confusion potentially. It's kind of a neat trick. Everybody's cool? All right, I'll do one more here. All right. So I have 1/3 natural log w minus 3 natural log x plus 2 natural log y minus 5 natural log z. First step is look for what? Power property. How many power properties do you see? 4. Remember that a fractional exponent is the same as a radical, so I'm just going to write w to the 1/3 already as the cube root of w. And then, as we mentioned earlier, we could also do the same thing with negative exponents. Okay. Just like we've done in the previous ones, let's do the left-hand side first, all the way to the finish, and then we'll come back and do the right side. Again, all of these we've done it 2 separate ways. Either you don't have to do it both ways. One way or the other is fine. Do whatever feels easiest to you. All right, we did powers. What's next? Product. How many product properties do you see? 1, okay. Between which logs? First and third. Can't fool you guys again. All that look good? Here's the thing though. I did fool you again because there is a second product property hiding here. Let me give you a hint. Let's go back and look, remind you of what happened in example C and when we expanded, where we had to distribute the negative. What's the opposite of distributing? Factoring. Notice what can we do on this problem here? Factor out a negative. Oh, Mr. Kulik. That's some sneaky stuff right there. Does that feel okay? Now there's the hidden product property that Mr. Kulik was referencing. Ugh. Ugh. Sneaky stuff, Mr. K. Sneaky stuff. And then we can apply our quotient property and we're finished. John.
So what if you already step 2
Mm-hmm.
before you did the factor of the
Mm-hmm.
negative? You did quotient between the first and third logs.
Okay, So you're saying that you would want to have done like this. Like somehow you've done like two quotient properties.
Wait, well, wouldn't it be Z5 first and then over X3? Then you have to do first and third.
Which, I'm sorry, so
If you do
you're back at this step here, right?
Yeah, that's
Okay. And you're doing the quotient between the first and the second?
the third.
The first and the third?
Oh, I guess you could do first and second as well.
Yeah. Yeah, I think either would be okay.
Yeah, and then you end up with that.
Yeah. So
That.
here's kind of what you'd have, right? So the way you'd want to think about this is not wrong. I'm going to think about it that way. Is that okay?
Yeah.
And when we divide fractions, we multiply by the reciprocal, and that's going to give you the same thing. So you could do it that way as well. Not wrong to do it that way. I think makes more opportunities to do something silly, like make a silly mistake. What we're going to find here in a moment is if we took the negative exponents with us, everything is like super clear as to what to do. So if we go back to the right-hand side here, we just see three product properties to use. And then just using the negative exponent property, we're done. That's a little nicer there. Again, you can go and do that in any route you want, but oftentimes, particularly with the problem has a lot of subtraction in it, like taking those negatives with the exponents can make life a little bit easier. Luke?
So if it's x to the negative third, then you're going to put that in the denominator.
Yep.
So if it was just x to the negative third, nothing else would be 1 over.
Yes. Correct. Yep. So the property that that we're using there is that one, I guess, for non-zeros x. Okay. One more thing to show you guys. So the fourth property that I didn't write was this change of base formula. Right, we wrote it last time, but I didn't write it today when I did my little recap. We're going to prove this real quick. Again, I think we proved the product property last time. I think I asked you to do some more of these proofs or prove some of these other properties in the homework, so I figure just giving another example would be kind of nice. All right, so what I'm going to do is I'm going to start by taking the right-hand side and setting that equal to, I don't know, some variable. Let's call it just capital A. The point of this is that I get a logarithmic equation. So by using my definition of logs, I can rewrite that as an exponential equation. Taylor? Of course. Cool with that? Now, if I look at my change of base formula, on the right-hand side, I need to get log base C of A. So to get that part of it, I'm just going to take log base C of both sides. So standard algebra technique where we do something to both sides of our equation. Cool with that? Take a look at this piece. What do you notice you can do with that? Power property. Very good. So that's going to give me A times log base C of B equals log base C of A. If I go back and I look at my change of base formula on the right-hand side, the denominator should be log base C of B. That is the coefficient I have on the right-hand side. So if I divide both sides by that, the right-hand side of my change of base formula is now complete. Cool. And hey, do you remember what we said A was equal to in the very beginning? Log base B of A. And that now is my change of base formula. Now that looked really easy when Mr. Kulik did it. That's not trivial to come up with on your own. There's some sneaky things that we did there. But in general, start by writing some logarithmic equation, convert it to an exponential equation, use some property of exponents or algebra or whatever to kind of get what you need. You know. That will close section 15.3. I forgot at the beginning of class to ask if there was homework questions, so let's do that now. Does anybody have questions from the homeworks? I think as of last time we're up to 70. Today we're going to ask you to do 71 to 78, but we're going to put that into the next week's problem set. So I think 1 through 70 is probably sufficient for this week. Bump that other stuff into next week's. Yeah, so Sunday is 1 through 70. The week after that is 71 through 98 plus whatever we get to next. But if you guys have homework questions, we can knock a couple of those out for you guys right now. We still got, I don't know, 15, 20 minutes. Luke?
So for 36C, when it's asking for the maximum number of deer in the park, would that just be the initial amount, so it'd be the 1,001?
Hold on, let me look here. So 1,001 is not the initial amount of deer, but that is the maximum carrying capacity for that population, yes.
So then what would be the initial population?
So the initial population, the time for initial is time 0. So I would just plug 0 in for t and evaluate that. So you'd get like 1,001 divided by 91, whatever that number is. 12 or something, I don't know.
And also, could you do 34?
34?
Yeah.
Okay. Yeah, the number of grams of carbon-14, denoted C, present in a certain substance after T yees, I don't know what a yees is. Anyways, is given by C of T equals yada, yada, yada. Use the equation to estimate the half-life of carbon-14. So half-life is the time it takes for half of the initial amount of substance to decay. So we know the initial is 20. So what I really just need to solve is this. Okay. Half of 20.
Oh.
Half-life is half the amount of the initial amount is gone. So we're going from 20 down to 10. Do you know what the significance of carbon-14 is? It is not. Normal carbon is carbon 12. We use carbon 14 in carbon dating, yeah. Very good. So carbon 14 is important because we can use it to date old objects, at least if they're made out of living materials. So you can figure out how long ago that living material died. And we can date carbon date things that are really old. Do you think the half-life is going to be a big value at T or a small value at T? Be big, right? Because we can date things that are thousands and thousands of years old.
Oh, yeah.
So the half-life should be really long. So I'm going to go 0 to 10,000 on my X, and then just 0 to 20 on my Y. So if I hit graph, that's what I get. Second, trace, intersect command, enter, enter, enter. So the half-life looks like to be about 5,700 years. Or I guess in this case it's yees, as quoted in the problem. I love the typos. It's so much fun to be just like super literal with like, clearly it meant years, but somebody forgot the R, so it's 10,000 yas. Maybe that's a yay. I don't know. Maybe Little John wrote the question. Is he the guy that's like, yes, right? No, that was a thing like 10 years ago.
And then do you mind doing 16C?
16C? Sure. Oh, I don't have 16. Let's grab it. Okay, okay. I see what the problem's going to be. Oh, 16C?
Yeah.
It's going to be just 19.875 million, though, because it's P of T is in millions.
Oh.
So it's 19.875 million people.
Okay. Yeah. I was reading comprehension.
They get you, don't they? You're not used to it in math class. You're just like symbol push, only symbol's important. Words don't matter. It's like, oh, darn it, the words mattered. Cool. Anybody else got questions on things or have things they want to talk more about? Cool, me neither. I'll call this a day. Thanks, guys.